Okay, so in today's lecture we are going to see kinetic energy correction factor and momentum correction factor, and the last point of your fifth chapter, that is dashpot mechanism. So before starting with what the exact derivations or the actual derivations, let us see what is the requirement of kinetic energy correction factor. So correction factor is something that covers up the error. Okay, if for example, in a circular pipe like this, it is designed for velocity 5 meter per second, that is your average velocity or design velocity. But after having implemented the design and actually using the pipe, you get velocity of 4.85 meter per second. That is the actual velocity that you are getting after observing the working of the pipe. So you tend to get an error of 0.15 meter per second. Okay, so that is the difference between the actual and the design velocity, and that is the error. So we need to identify such a factor which will help us to reduce this error or correct our or bring in accuracy in our velocity or any design parameter. So similarly, in case of kinetic energy, which is a function of velocity, as the actual velocity and design velocity will differ on the similar lines, kinetic energy will also differ. In the design kinetic energy will be different, the value of design kinetic energy will be different, and that of the actual kinetic energy will be different, and therefore there will be some error, and to cover up that error we have to come up with a correction factor which will help us in reducing that error. So that is called as kinetic energy correction factor, and it is denoted as alpha. Okay, so alpha is equal to kinetic energy correction factor, which is equal to kinetic energy per second based on actual velocity upon kinetic energy per second based on average velocity. Okay, so consider a circular pipe, okay, with a center line like this, whose radius is capital R, and consider a circular elemental ring of radius small r, and thickness dr. So the this cross section area of this circular elemental ring will be equal to dA, which is equal to 2 pi r into dr, circumference into the thickness of the elemental ring. And at the cross section you can see that the velocity varies parabolically. Okay, u max being at the center and u0 at the surface. Okay, so now we'll start with the actual derivation. We can say that kinetic energy of the fluid passing through the ring of thickness dr as kinetic energy is equal to half mv square. Therefore, so this kinetic energy is meant for the entire pipe cross section. So for the kinetic energy just limited to this elemental ring will be equal to dE. Okay, so it is equal to half m into rho dq into u square. Now why rho dq in this case? Because m is equal to mass per second is equal to rho into discharge q. Why? Because kg per meter cube into meter cube per second is equal to kg per second, which is equal to mass per second. Therefore, we have written rho into dq we have substituted m with rho into dq, and v square is equal to u square. Why u square? U is the local velocity, and as we have considered the elemental ring at any position at a distance radius small r away from the center, so at any location within the cross section of the pipe, the local velocity at that very location will be u, small u. Therefore, dE is equal to half into rho into dA into u square. Now dq is equal to dA into u, that is area into velocity, a into v. Therefore, we already know that dA is equal to 2 pi r into dr. Therefore, dE is equal to half into rho into 2 pi r dr into u square. Therefore, dE is equal to rho pi r u cube into dr. Okay, so this is the kinetic energy represented for an elemental ring within the cross section of the pipe. So it is not this expression does not indicate the kinetic energy for the entire cross section of the pipe. Okay, it is just meant for the small elemental ring. So now we are going to integrate this from 0 to r, capital R, to find out the kinetic energy across the entire cross section of the pipe. Okay, so we have this expression that dE is equal to rho pi r into u cube into dr. Now u is equal to 1 by 4 mu minus dou p by dou x into capital R square minus small r square. Since therefore your dE is equal to rho pi r into 1 upon 4 mu minus dou p by dou x into capital R square minus small r square cube dr. Okay, now integrating it between 0 to r, one upon 4 mu minus dou p by dou x so that is the expression. Therefore, further we can write it as E for energy is equal to, take the constants outside, R into, and take the cube of these two terms, so you get 1 upon mu cube to 64 into minus dou p by dou x cube into r square minus r square cube into r into dr. Therefore, E is equal to rho pi into 1 upon 64 mu cube into minus dou p by dou x cube r square minus small r square cube r dr. So now you have to expand this as identity, which is equal to a square minus a minus b bracket raised to 3. Therefore, it looks like this. Therefore, E is equal to rho pi into 1 upon 64 mu cube into p by dou x cube. So you can write it as r raised to 6 plus r raised to 6 minus r raised to 6 minus 3 r raised to 4 r raised to 2 plus 3 r raised to 2 r raised to 4. okay, into r dr. Therefore E is equal to rho pi into 1 upon 64 mu cube minus dou p by dou x cube into r raised to 6 into small r raised to minus r raised to 7 minus 3 r raised to 4 r raised to 3 plus 3 r raised to 2 r raised to 5 dr. Therefore E is equal to rho pi upon 64 mu cube minus dou p by dou x r raised to 6 r raised to 2 upon 2 minus small r raised to 8 upon 8 minus 3 r raised to 4 small r raised to 3 4 upon 4 plus 3 r raised to 2 r raised to 6 upon 6. Therefore E is equal to rho pi upon 64 mu cube minus dou p by dou x cube into r raised to 8 upon 2 minus r raised to 8 upon 8 minus 3 r raised to 8 upon 4 plus 3 r raised to 8 upon 6. Therefore E is equal to rho pi 64 mu cube minus dou p by dou x cube. So we have this answer as 24 r raised to 8 minus 21 r raised to 8 upon 24. Therefore E is equal to rho pi 64 mu cube minus dou p by dou x cube into r raised to 8 upon 8. So this is your first equation, that is the kinetic energy because of actual actual velocity. Kinetic energy because of actual velocity. Now kinetic energy based on average velocity is equal to half mass into u bar square, as kinetic energy is equal to half mv square. So now in this case we are taking v as your average velocity is equal to half into rho into area, rho into q into u bar square, because mass is equal to rho into q. Therefore kinetic energy is equal to half into rho into area into velocity into, because q is equal to a into v, a into u bar. Therefore ke is equal to half rho a u bar cube. Now your u bar is equal to 1 upon 8 mu minus dou p by dou x into capital R square, and a is equal to pi r square. Therefore kinetic energy based on average velocity is equal to half into rho into pi r square into 1 upon 8 mu cube minus dou p by dou x cube into r raised to 6. Okay, so we have taken the cube of this entire expression. Therefore kinetic energy is equal to half into rho pi r 8 raised to 8, this r square into r raised to 6 into 1 upon 64 mu cube into 8. 8 square is 64 and the remaining third 8 has been kept as it is into minus dou p by dou x cube. Therefore kinetic energy is equal to rho pi r raised to 8 upon 2 into 64, 128 mu cube into 8 into minus dou p by dou x cube. So this is the equation 2, and it is the kinetic energy per second based on average velocity. Therefore, now alpha, based on the definition, as the ratio of kinetic energy per second based on actual velocity upon kinetic energy per second based on average velocity. So the expression that we have got, the first expression is equal to alpha is equal to ratio of equation 1 to equation 2. Therefore, alpha is equal to rho pi upon 64 mu cube into minus dou p by dou x cube into r raised to 8 upon 8 upon rho pi r raised to 8 upon 128 mu cube into 8 minus dou p by dou x cube. So rho pi 64, this is 2 za mu cube, okay, and r raised to it. So we are left with 1 upon 8 upon 1 upon 16. So it is equal to 16 upon 8, that is equal to 2. Therefore, kinetic energy correction factor is equal to 2 for circular pipes. So that is our first derivation of kinetic energy correction factor. And the second part is similar part wherein which is also function of velocity. Okay, so that is the momentum. So in the next part, next derivation, we are going to find out the correction factor for momentum, which is a function of velocity again. And again, for circular pipe, if the design velocity and the average velocity, they are going to differ because of some actual live conditions, then that error has to be overcome that is caused in the calculation of momentum, and therefore we have to find out a correction factor which is based on actual velocity and average velocity. Okay, therefore momentum correction factor, which is denoted as beta, which is equal to momentum per second based on actual velocity upon momentum per second based on average velocity. So we are going to consider the same diagram, this one, where we have considered a circular pipe with a radius capital R and a elemental ring whose radius is small r with thickness dr. Therefore, the cross-section area of this elemental ring is 2 pi r dr. Okay, so now we have momentum is equal to mass into velocity. Okay, so mass is equal to rho into dq into your local velocity, because we are going to find out momentum due to actual velocity u or local velocity. Okay, now rho into dA into u. So this is equal to area into local velocity. Rho into 2 pi r dr into u square, momentum. Let us write it as dm for elemental ring, for circular elemental ring. Okay, now if we integrate this from 0 to r, we get 2 pi r into rho into u square dr. Okay, but u is also equal to 1 upon 4 mu minus dou p by dou x into capital R square minus small r square. Therefore, your m is equal to 0 to r into 2 pi r into rho into 1 upon 4 mu minus dou p by dou x into small capital R square minus small r square whole bracket square into dr. Therefore, m is equal to 2 pi rho into 0 to r into 1 upon 4 mu square minus dou p by dou x square to r square minus r square bracket square into r into dr. Therefore m is equal to 2 pi rho upon 16 mu square into dou p by dou x square. Now this is a minus b bracket square. This looks like this is identity. Therefore r raised to 4 minus 2r square small r square plus small r raised to 4 into r dr. Therefore m is equal to 2 rho pi upon 16 mu square minus dou p by dou x square into r raised to 4 into small r plus 2r square r raised to 3 minus plus r raised to 5 dr. Therefore m is equal to 2 rho pi upon 16 mu square minus dou p by dou x square into r raised to 4 r square upon 2 plus minus 2 r square r raised to 4 upon 4 plus r raised to 6 upon 6 0 to r. So further upon simplification you get m is equal to 2 rho pi upon 16 mu square minus dou p by dou x square to r raised to 6 upon 2 minus r 2r raised to 6 upon 4 plus r raised to 6 upon 6. Therefore m is equal to 2 rho pi upon 16 mu square minus dou p by dou x bracket square on 12r raised to 6 minus 4r raised to 6 plus minus 12r raised to 6 upon 24. Therefore m is equal to 2 rho pi upon 16 mu square minus dou p by dou x upon r raised to 6 upon 6. Therefore m is equal to rho pi upon 48 mu square into r raised to 6 into minus dou p by dou x square. This is your first equation. Momentum based on actual velocity. Now momentum based on average velocity u bar. So momentum is equal to mass of fluid per second into velocity, mass into velocity. M is equal to rho a u bar into u bar. Now u bar is equal to u max upon 2. Therefore u for m is equal to rho into a into u max upon 2 square. Now a is equal to pi r square. Therefore m is equal to rho pi r square into u max upon 2 square. U max is equal to 1 upon 4 mu minus dou p by dou x into capital R square. Therefore m is equal to rho pi r square upon 4 into 1 upon 4 mu into minus dou p by dou x into r square bracket square. This 4 comes from the square of this 2. Therefore m is equal to rho pi r square upon 4 into 1 upon 16 mu square into minus dou p by dou x square r raised to 4 for m is equal to rho pi r raised to 6 upon 64 mu square into minus dou p by dou x square. This is your equation 2. Momentum due to average velocity. Therefore your beta is equal to momentum correction factor is equal to ratio of equation 1 to 2. Therefore beta is equal to rho pi r raised to 6 upon 48 mu square minus dou p by dou x square upon rho pi r raised to 6 upon 64 mu square minus dou p by dou x bracket square. So all these terms get cancelled. You are left with 64 upon 48, which is equal to 4 by 3. Therefore momentum correction factor for circular pipe is equal to 4 upon 3. Thank you.